In today's lesson, we're going to be learning about how complex numbers function as solutions to polynomial equations. It turns out that complex numbers really found their historical roots in solving polynomial equations, and today we're going to learn about how some of the properties of complex numbers will help us to solve these polynomial equations. So before we get started, let's go ahead and take a deep breath. And let's begin. As you likely know, when we move into new topics, we very often have to clarify or define some vocabulary. The vocabulary I'm talking about at the moment are these four words right here: root, zero, solution, and factor. And the reason I want to spend some time talking about them is I fear that they are sort of close to one another in your minds, and you may be, in fact, so close that you feel like they're interchangeable, but they're not. They are slightly different from one another, and so I want to make sure that we're clear on what these words mean. So a zero or a root of a polynomial, these are two words that are more or less interchangeable. A root or a zero is a value that you can input into a function that causes that polynomial or function to give you an output of zero. That's why it's called a zero, right? And sometimes we call it a root. The terms root and zero are more or less interchangeable. I will say that I tend to use the word root when I'm talking about polynomials, and I tend to use the word zero for non-polynomial functions like natural log or e to the x. So next, there's a solution. Okay? A solution to an equation is also a value. It's a value that you can input into the equation that causes the equation to be true. Now, you may have noticed that, that both of these are values. They're both values that are input into something, right? But one of the main differences is that a solution is something that is applied to an equation, whereas roots or zeros are something that are applied to a function or a polynomial. So basically, you can't find a solution to x squared minus 4x plus 5. There's no solution to this because it's not an equation. But for what it's worth, x squared minus 4x plus 5 could have, or in fact does have, roots or zeros, right? Because it's a polynomial or it's another function. The final definition that I want to throw out here is that of a factor. Okay? A factor, particularly of a polynomial, a factor of a polynomial is a monomial or polynomial that divides into the given polynomial. Right? So for instance, if we had x squared minus 4x plus 3, which we know factors into x minus 3, x minus 1, x minus 3 is a factor of this polynomial. X minus 1 is a factor of this polynomial. So just to be clear, the words root, zero, and factor apply to polynomials, and a solution applies to an equation. I would encourage you all to really work carefully to try and use these words sort of properly and precisely as we move through this lesson. So just to practice that, let's consider this example where we'll get an opportunity to use these vocabulary terms. So consider this polynomial. First, I want us to solve this polynomial equation, and then use the terms zero, root, solution, and factor properly as they apply to the problem. So go ahead and pause the video and try this out, and then we'll come together and check it. So to factor this polynomial, many of you sort of use this method where you want to find two numbers that multiply for -6, that's -2 times 3, and add for -5. So those two numbers are -6 and +1. And then you sort of, build your box off of this to figure out how this is going to come apart. So you'll have 3x squared here, -2 here, and then you put these two numbers, you sort of use them to construct these. And then you're going through and sort of pulling out what these factors are. So if these two things have a 3x in common, then this would have to be x, and this would have to be -2, and then this over here would have to be +1, and then we sort of double check, yep, those things work. Great. So we know that the factors of 3x squared minus 5x minus 2 are 3x plus 1 and x minus 2. So next we might think about the idea of solutions, right? If these are the factors, it means that 3x plus 1 times x minus 2 equals 0, because we're told that we're supposed to solve the equation p of x equals 0. So I'm taking the factored version of p of x, I'm setting it equal to 0. We can then use the zero product property 3x plus 1 has to equal 0, and x minus 2 has to be 0. And that means that x equals negative 1/3 and x equals 2. If we move this up, so now we're going to practice using more of this vocabulary. So we could now say that the solutions to p of x equals 0. Notice I'm saying that it's solutions to an equation. The solutions to this equation are x equals negative 1/3 and x equals 2. Right? And then just to be clear with the roots and zeros, the roots or zeros of p of x, notice that I'm saying roots and zeros of a polynomial, not of an equation. The roots of this thing are the same thing as the solutions. It's a negative 1/3 and x equals 2. So I want to be clear. Roots and zeros are not the same thing as the solutions. But if you have the solution to a polynomial equation being 0, those will be the roots or the zeros of the polynomial. I'll admit that it's a subtle difference, but particularly as we continue to move toward our math exploration and our mathematical writing, it's important that we know how to use these terms precisely. So now that we've got that vocabulary cleared up, I want to move on to a couple of really important key points that are going to sort of lay the foundation for the work that we're doing in the lesson today. So if a is a root of the polynomial p of x, then x minus a will be a factor of that polynomial. So it's really, really important that there's this idea that roots and factors are connected to one another. Sometimes I'll even call x minus a the related factor of this root. Okay. Now, sometimes you've got a root that's a fraction, and so I just like to mention this separately to make it clear for everyone. If b over a is a root of a polynomial, then the related factor could be either x minus b over a or ax minus b. And these are effectively the same thing. It's just that in this one, you're sort of factoring an a out of it to get this. And remember that a is going to be a constant. So really, either one of these things can be factors. It's not like in some problems it's one and in some problems it's another. It's really just a question of whether you want to deal with a fraction that's inside here or sort of go for this preferred, we're working with all whole numbers. So now let's go ahead and sort of practice this principle with an example that's fairly simple. Now, funny story, I've actually got an example right here of even me misusing this vocabulary. I just mentioned that roots apply to polynomials and functions and not to equations. So my example shouldn't say find a quadratic equation with these roots. It should say find a quadratic polynomial. So find a quadratic polynomial that has those roots. So now that I've fixed it, let's do that. So if I have a root of 5, what factor is related or associated to that? Well, it would be the factor x minus 5. And if I have the root 3i, the factor that's associated with that is x minus 3i. And so now to find this quadratic polynomial, I just need to multiply these factors together. X minus 5 times x minus 3i. So when I multiply those, I'm going to get x squared minus 3ix minus 5x plus 15i. And there it is. Here's my quadratic polynomial that has those roots. Now this, you might feel weird calling this a polynomial because it has I in it. That's okay. That just means that this is a complex quadratic polynomial. And we tend to deal with real polynomials. And with that in mind, I actually have some specific things to tell you about real polynomials. But before we get to that, let's do one more example that lets us practice this relationship between roots and factors. So here I'm going to ask you to solve the equation x squared minus 6x plus 34, and then hence factor this. So you might notice that this doesn't actually factor. So because this doesn't factor, the only way for us to solve this is by using the quadratic formula. Now, personally, I really prefer the quadratic formula, but I'm going to go ahead and do it by completing the square because we may not have seen that in a while. So the idea on completing the square is that, assuming that this first coefficient is 1, what you're doing is you're taking half of this middle term and squaring it, which would be plus 9. Right? So then what many people do is they'll do that, and then they'll just add a 9 to the other side so that the equation stays balanced. So my original equation here was x squared minus 6x plus 34, and I'm just adding 9 to both sides. In doing that, this thing here is a perfect square trinomial. I can express it as x minus 3 squared, and then I could subtract the 34 to the other side and get negative 25. I then square root both sides. This gets me x minus 3 equals plus or minus, and now we can take the square root of a negative number. This would be 5i, and so here I'm going to have x equals 3 plus or minus 5i. So now that I know what the solutions are, it means that the roots, or the zeros, of this polynomial are 3 plus 5i and 3 minus 5i, and that means that we can factor it by writing x minus 3 plus 5i and x minus 3 minus 5i. And that's it, we factored it. So this again is sort of an example of the sort of relationship between solutions to an equation, roots and zeros of a polynomial, and then factors of that polynomial. One thing that I'm going to mention here, when you have complex roots like this, it's really important that you remember that this minus is applying to the entire root. And so you've got to put parentheses there. If you want to, you can immediately distribute that negative through, that's fine. You can make this x minus 3 minus 5i, and then x minus 3 plus 5i, but you're only going to get to that if you remember that you have these parentheses. All right, now I mentioned that I was going to talk about some special properties of real polynomials. So first, a real polynomial is just a polynomial whose coefficients are all real. So for the remainder of what I'm going to be talking about today, I'm going to be talking about real polynomials, so polynomials that don't have any imaginary numbers in the coefficients. They might have imaginary or complex roots, but the coefficients are all going to be real. So the first big theorem that we're going to learn today is called the conjugate root theorem. So assuming that you have a real polynomial, a polynomial with real coefficients, if z is a root of that polynomial, then z star will also be a root of that polynomial. In other words, for real polynomials, roots will always come in what are called conjugate pairs, which we learned about in one of the previous lessons. Now remember, this only applies to real polynomials, but when you have a real polynomial, it means that if 3 minus 2i is a root, then immediately you'll know that 3 plus 2i is a root. Keep in mind, this is only for real polynomials. Okay? So, for example, if I had negative 1 plus 4i, what other root would immediately be a root for us? It would be negative 1 minus 4i. And these would both be roots. Okay, the conjugate root theorem is like huge in terms of what we can do and the ways that we can sort of factor and break down polynomials. One more big theorem that I want to throw out here is called the fundamental theorem of algebra. Okay, and it turns out that this one does apply to both complex and real polynomials. The fundamental theorem of algebra just says that if you have a polynomial of degree n, it will always have exactly n roots. Some of those may be repeated roots, but it will always have n roots. So what that sort of means is that if you have an x to the 5th polynomial, x to the 5th plus 5x to the 4th plus 2x minus, whatever, this can be broken down into 1, 2, 3, 4, 5 factors. You will always be able to find exactly 5 factors. Each of those 5 factors will provide you with one root. The fundamental theorem of algebra is something that we literally did not have until imaginary numbers were, I don't want to say discovered, I don't want to say found, until they were formalized effectively in the 1700s. So the fundamental theorem of algebra is something that's newish to mathematics. So now that we have the conjugate root theorem and the fundamental theorem of algebra, two really, really strong, powerful results in the field of algebra, I'm going to move into one more basic skill, and then we're going to sort of apply this to some real problems. So because we have the conjugate root theorem, it means that we're going to be multiplying together conjugate roots quite often. In fact, we're not going to be multiplying conjugate roots. We're going to be multiplying conjugate root factors often. And because of this, I want us to have an efficient method for multiplying these roots. There was a student of mine that I had at this point, it was several years ago, that sort of noticed this pattern. And from that point on, it's been so much easier for me and for all of my students to multiply these factors. Yeah, just realized this should actually say factors. So, this example, consider a real quadratic polynomial, p of z, that has a root of 3 minus I. So my first question here, write down the factor that's associated with 3 minus I. So the factor that's associated with this would be z minus 3 minus I. And you might wonder, why did I decide to use z? Well, this right here says p of z. Commonly, z is going to be used for complex numbers, so that's where that came from. And I kind of want to take this and write this as, as z minus 3 plus I. Okay, so that's the factor associated with that. Now part B, find the other root and the other factor of p of z that are guaranteed by the conjugate root theorem. So what other root do you know that we have to have? We have to have the conjugate. We have to have 3 plus I. So the factor is z minus 3 plus I. And again, I want to write that like I did above, z minus 3 minus I. Now part C, I want us to do what we did in the previous example, right? I want us to multiply together these two factors to find this polynomial. So that means I need to multiply z minus 3 plus I by z minus 3 minus I. Now what you could do here is you could do a little box diagram, like a 3 by 3 box diagram, but I don't know, that's just going to be tedious, and especially if we're doing this a lot, it's a lot to do, to put the z minus 3 plus I and the z minus 3 minus I and multiply out all 9 of those boxes and then find the like terms and all of that stuff. So there's a really, really, really neat thing in here. If you look closely, you'll see that there's like a difference of squares pattern that's happening. Do you see how this is z minus 3 plus I and then z minus 3 minus I? So if I had given you z plus 5, z minus 5, I don't know that you guys would have multiplied this out. I think you would have realized, oh shoot, that's just z squared minus 5 squared. So similarly over here, it means that this can be multiplied together by doing z minus 3 squared minus I squared. And because we've had so much experience with both of these things, this is really fast. Z minus 3 squared is going to be z squared minus 6z plus 9 minus I squared is negative 1, and boom, it's z squared minus 6z plus 10. It turns out that this thing is always going to work out this way, and so we can always use this trick when we need to multiply together two of these factors that have come from complex conjugate roots. The final two examples in this lesson are going to utilize that sort of shortcut trick that I just showed you for how to multiply together two factors of a conjugate root pair. So make sure that was clear to you before you get into these. I'd encourage you, if possible, to try and work through this one on your own. If you're really unsure, I'll go ahead and get you started on it and then let you finish it. So you're being asked here to find the real polynomial p of z. Remember that a real polynomial is a polynomial with real roots. I'm sorry, not with real roots, but with the real coefficients. You're looking for the one that has lowest degree, which has the roots of z equals 2 and z equals 1 minus 3i. So pause the video, try this one on your own. If you're unsure, I think the hint that I would give you is, if you're given roots, then you should be able to find factors that go along with those roots and then multiply those factors together to find this. Remember, you also have the fundamental, not the fundamental theorem of algebra, but the conjugate root theorem that says if this complex root is one of the roots, then you should know another one for free. So because of this one, we also know that z equals 1 plus 3i by the conjugate root theorem. Okay? And so because of that, we know that we can write these things all as factors. Z equals 2 is going to give us z minus 2. This next one is going to give me z minus 1 minus 3i. And then I also have the one for its conjugate pair, 1 plus 3i. So I'm going to focus on these two complex ones first. This is z minus 1 plus 3i, and z minus 1 minus 3i. And I still have this z minus 2. I'm going to deal with that later. Over here, I want to use that trick that we just learned. I want to recognize that this is z minus 1, and then plus 3i and minus 3i. So I want to see this as z minus 1 squared, and then minus 3i squared. And again, I'll still have the z minus 2 out here. So working with the thing that's out here, this is z squared minus 2z plus 1 minus 9i squared, but I squared is negative 1, so this becomes plus 9. Still have my z minus 2 that's waiting for its turn, and then z squared minus 2z plus 10, and finally this z minus 2 is going to get its turn. Now that I've finally done this, I'm going to go through and multiply these things together. Some of you use a box method for this. Some of you just sort of use the drawing the lines and multiplying this together method. I'd encourage you to use what works for you, but your focus should be on accuracy. Please don't make your focus on how do I use the least paper, or I don't really want to write down very much. If you're this far into the problem, you might as well do it right. So if you want to go about using like a box method for this, you might write this out, put z minus 2, z squared minus 2z plus 10. And then let's see here, we'd have z cubed minus 2z squared minus 2z squared, positive 4z, positive 10z, and then negative 20. And then as we pull this together, z cubed minus 4z squared plus 14z minus 20. And there it is. This is my polynomial, my cubic polynomial that has those roots that were offered earlier in the problem. Here's our final example of the lesson, which is sort of being asked in a slightly different way. In this case, we're being given a polynomial that might be really difficult to factor. We're generally not very good at dealing with cubic polynomials or quartic or higher degree polynomials, but the IB exam will often ask us to factor them, and the way they do it is by giving you enough information to help you sort of crack this thing down to being a quadratic, or even smaller than that sometimes. So I'd like to encourage you to work through this problem on your own. If you're not sure, I'll sort of give you a hint here in just a moment. The hint that I would give is this is a real polynomial, we can tell. Because of that, the conjugate root theorem should tell us that we know another root. And because of that, I can convert these things into factors, and if those are factors of this, it means they should divide into that. And if you can divide into that, I bet you can start factoring and breaking it apart. So now that we've sort of got a sense for what our strategy is here, this thing is going to give me a factor of z minus 2 minus I root 3. But the conjugate root theorem tells me that 2 plus I root 3 should also be a root, so we need a factor for that one too. Z minus 2 plus I root 3. And then I'm thinking, well, if both of these are factors of this, then whatever they multiply together to should also be a factor of this. So I'm going to multiply these things together and then divide it into what I have here. I'm going to use the same trick I did before where I sort of expand these things out, or at least distribute what's inside of them. And then once I've done that, I'd like to notice that sort of difference of squares-ish pattern, z minus 2 plus I root 3 and z minus 2 minus I root 3. Because I have that, I know that this is going to be z minus 2 squared minus I root 3 squared. And then I can expand these, right? The inside of this is z squared minus 4z plus 4, and then minus I squared times root 3 squared, which is 3. But the I squared is negative 1, which will make this plus, so this becomes z squared minus 4z plus 7. Now all I have to do is find out how many times does this divide into this. My suspicion is that most of you are going to want to do that division by using something like Polydoku, or sort of the backwards box method kind of thing. So the idea there is that you're looking at it saying, well, I know that this cubic, I know that this 2z cubed minus 13z squared plus 34z minus 35. I know that that thing is supposed to be z squared minus 4z plus 7 times something. So I'm going to sort of put what I know of this into here, figure out what this is, and sort of check and make sure that the middle stuff all works out. So if I know that this first thing up here has to be 2z cubed because of this, it sort of forces this to be 2z. And if I know that the end of this has to be negative 35 because of this, it forces this to be minus 5. So we could maybe conclude, oh, then it means that 2z minus 5 was the thing it was. But if this middle part doesn't work out, it means we made a mistake up here, or it means that I made a mistake writing the problem. So let's kind of go back through and check this, right? This term would be negative 5z squared, and this would be negative 8z squared. These two things together make negative 13z squared, which matches what I have here. So that's good news. When I move on to this other one, this is negative 14z, and this is, oh, I'm sorry, that's positive 14z, and this is 20z. Those two things together make positive 34z, which also checks out. So now we need to make sure we answer the question. The question was saying find all of the factors, and it was saying find all the roots and then completely factor the thing. So if I want to find all the roots, it looks like my roots are, well, let's see, this one, 2z minus 5 is going to yield a root of 5 halves. So we have 5 halves, we have the one that they gave us, and then the one that we implied from the conjugate root theorem. And then the final part is they asked us to factor this thing. Looks to me like it factors to be 2z minus 5 times this one, z minus 2 minus I root 3, and then finally times this one, 2 minus 2 plus I root 3. So we were able to take a cubic polynomial that we might not normally have been able to factor, and by using the one thing that they gave us, we were able to chip apart the whole thing. So I hope all of that made sense. As always, if you have questions, please let me know, and of course, best of luck as you work through the assignment.